Hello and welcome again to my video on this channel. So before proceeding the video, a special welcome to those who are new to the channel, and if you are new to the channel, please make sure that you subscribe to the channel and press the bell icon so that you can get notifications about new and upcoming videos on Python. And as I have said, once Python series is complete, we will proceed to learn HTML, CSS, JavaScript, and then we will come back to Python where we will learn web development using Flask, Django, and FastAPI and so on. So we will continue where we left off in previous video, and we were discussing int, float, complex types. We were discussing hashing of the uh, objects. We had completed all this. Yes, we had completed up to here. So the hash functions, we visited this link and we completed this. So we can continue from here. For ease of implementation and efficiency across a various type of numeric types, including int, float, decimal, dot decimal, and fractions, dot fraction, Python's hash for numeric types is based on a single mathematical function that is defined for any rational number and hence applies to all instances of int, fractions dot fractions, and all finite instances of float and decimal dot decimal. Essentially, this function is given by reduction modulo p for a fixed prime. The value of p is made available to Python as the modulus attribute of sys.hashinfo. So in C Python on 32-bit systems, this prime p is 2 to the power 31 minus 1, and on 64-bit is 2 to the power 61 minus 1. Such kind of primes are known as not Mersenne primes. Mersenne primes occur in pair, but they are one part of Mersenne prime. Okay. So the rules are given in detail here. How hash is computed. If x is equal to m by n is a non-negative rational number and n is not divisible by p, then define hash x as m into inverse mod n comma p percentage p, where in mod n comma p gives the inverse of n modulo p. If x is, I'll let you do the math. I'm not doing the math here for you, at least not in programming videos, but all right, I'll do it. So suppose this is our fraction, and for most common integers n would be 1 and n would not be divisible by p. Okay, so it would be m into, let's say the number is 5, so 5 into inverse mod n comma p percentage p. So n is 1 here and p is 2 to the power 61 minus 1 on 64-bit. So inverse mod would be inverse of n modulo p. So 5 modulo p would be 5, and inverse of that is 1 by 5. So this will become 1 by, sorry, n would be 1. So it would become p by n, that is 2 to the power 61. And 2 to the power 61 p, that is when a remainder is required, it would become 0. Hang on. So now n comma p inverse mod. So n modulo p would be 1, and inverse of that would be 1. Okay. So m into 1 percentage p would give us m. As long as our n is 1, the hash of m would be the number itself, provided it is less than 2 to the power 61 minus 1. If x is equal to m slash n is a non-negative rational number and n is divisible by p but m is not, then n has no inverse modulo p and the rule above does not apply. In this case, hash x to be constant value sys.hashinfo.inf. If x is equal to m slash n is a negative rational number, define hash x as minus hash minus x. If the resulting hash is minus 1, replace it with minus 2. The particular values sys.hashinfo.inf and minus sys.hashinfo.inf are used as hash values for positive infinity or negative infinity respectively. For a complex number z, the hash values of real and imaginary parts are combined by computing hash z.real plus sys.hashinfo.imaginary multiplied with hash z into imaginary reduced modulo 2 to the power sys.hashinfo.width, so that it lies in the range minus 2 to the power sys.hashinfo.width minus 1, comma 2 to the power sys.hashinfo.width minus 1. Again, if the result is minus 1, it is replaced with minus 2. To clarify above rules, here are some example Python code equivalent to built-in hash for computing the hash of a rational number. So suppose a fraction comes m comma n, then this is the logic which is used to compute the hash. So what we do is first we find out p, that is the modulus. And if m percentage p is equal to n percentage p is equal to 0, then m comma n is equal to m integer division p and integer division p. If n percentage, and now it is while, so it finds the common factors of p. Now if n percentage p is equal to 0, hash value is sys.hashinfo.infinity. Now hash value is absolute m, it's absolute value of m percentage p multiplied with n comma p minus 2 comma p percentage p. So this is the hash value. If m is less than 0, hash value is negated. If it is minus 1, then you replace it with minus 2 and return the hash value. Here it is demonstrated how hash value of a float is constructed, and here we are shown how hash value of a complex number is computed. So now we look at Boolean types. Booleans represent truth values. The bool type has exactly two constant instances, true and false, which we have seen in built-in constants. The built-in function bool converts any value to a boolean if the value can be reinterpreted as a truth value. Truth value testing we have already studied, where we have studied what values qualify as false. For logical operations, use the boolean operators and, or and not. When applying the bitwise operators ampersand, pipe and caret to two booleans, they return a boolean equivalent to the logical operations and or XOR. However, the logical operators and or not is equal to should be preferred over ampersand, pipe and caret. Bool is a subclass of int. So this is deprecated, by the way, deprecated since 3.2. The use of bitwise inversion operator is deprecated and will raise an error in Python 3.14. So tilde bitwise negation is no longer there. Bool is a subclass of int. See numeric types int float complex. In many numeric constant context, false and true behave like integers 0 and 1 respectively. However, relying on this is discouraged. Explicitly convert using int instead. So you should not treat booleans as 0 and 1. Now we look at some iterator types. We have seen quite a few of them when we were going through our built-in functions. So this is something which is given in detail here. Python supports a concept of iteration over containers. This is implemented using two distinct methods. These are used to allow user-defined classes to support iteration. Sequences described below in more detail always support the iteration methods. One method needs to be defined for container object to provide iterable support, and that is container.iter method. This method returns an iterator object. The object is required to support the iterator protocol described below. If a container supports different type of iteration, additional method can be provided to specifically request iteration for those iteration types. An example of an object supporting multiple forms of operation would be a tree structure which provides both breadth first and depth first traversal. This method corresponds to the TP iter slot of the type structure for Python objects in Python C API. The iterated objects themselves are required to support the following two methods, which together form the iterator protocol. So those two functions are underscore underscore iter underscore underscore and underscore underscore next underscore underscore. So the iter function returns the object itself. This is required to allow both containers and iterators to be used with the for and in statement. This method corresponds to the TP iter slot of the type structure for Python objects in the Python/C API. Next returns the next item from the iterator. If there are no further items, raise the stop iteration exception. This method corresponds to TP underscore iter next slot of the type structure for Python objects in Python/C API. Python defines several iterator objects to support iteration over general and specific sequence types, dictionaries, and other more specialized forms. The specific types are not important beyond their implementation of the iterator protocol. Once an object's next method raises stop iteration, it must continue to do so on subsequent calls. Implementations that do not obey this property are deemed broken. So we will study next generators and then we will stop. So Python's generators provide a convenient way to implement the iterator protocol. If a container object setter method is implemented as a generator, it will automatically return an iterator object. We have also studied generators when we were studying the yield keyword earlier in the language discussion. So iterator object is technically a generator object supplying the iter and next method. More information about generators can be found in the documentation for the yield expression. So when we discussed the yield expression, we studied this. So if you want, you can study this in the language description section of Python documentation. So if you want to learn language, then you should go and study this. I have covered most of this in the form of examples already in earlier videos. There are 30 plus videos, so these are covered there. So I'll stop here, and tomorrow onwards we will study sequence types, and there will be lots of examples for list and these types, and we will see them in a lot more detail. So you can see that not enough examples are given. We will create examples and test these functions when we study the sequence types. So first we are studying list, tuple, and range. These three sequence types we will study. So I hope that you have found useful as we read through the documentation of Python standard library, and I hope that you find it useful to study with me. So please like the video, share it as much as you can on social media, and make use of comment box to voice your opinion so that we can interact together and learn from each other. In any case, your watching video is very motivating to me, even if you don't subscribe or like or share or comment. Just watching is a great motivation to me. Thanks a lot for watching. Happy programming.